Hey guys, today I'll be doing LeetCode number 69, square root x, which is an easy question. This question requires, well, you could cheat your way through and just do a square root function on the answer and you would get the closest value, just floor it. But the other way to do it is by using this thing called binary search. Now what is binary search, right? Imagine we are playing a game of guess the number, and I give you a range that my number will be from 1 to 100, and every number you guess, I'll either tell you high or I'll tell you low, right? And the most inefficient way to do it would be to go one by one. So you would guess 1, then you would guess 2, and let's say the number I've guessed is 70. Then if you guess 1, 2, 3, and I went higher, right? You would eventually be like, you would guess 70 times before you would actually get the answer, right? And this is like pretty bad. Like, the amount of times you're guessing, there's a better way to do it. So another way to do it is, what if we hit it directly on the middle of the range? So from 1 to 100, if we go for 50, now we compare that with 70, I'll tell you higher. But by saying 50, what you've done is, for numbers 1 through 50, now that I've said higher, you don't need to guess these numbers because they will never be them, right? Because 50 is the highest in that range, and since I've said it's higher than 50, then anything lower than 50 won't work. And the next way to halve it is, so now we have a range 50 to 100, we'll halve it by saying 75. Now I'll tell you lower. So now you can say, okay, so it's going to be 50 to 75. 51, sorry, actually. Because if it is the guess, then we returned it. There you go, 51 to 75. 51 to 75. Now the number lies in between that. We'll take the middle of that again, 51 plus 75. We'll divide it by 2. So 126 by 2. So 63. We'll say 63. I'll say higher. And then we go 63 to 75. And then we get 138 by 2. Now once you, I won't show it all, but once you repeat it, you'll eventually get to 70. And the idea is, you would get there in basically half of the steps that you would be taking from here, right? And that's essentially what binary search is. You cut half the array from your guesses, so your searching is effectively half. So searching now takes half the time. And another way to, not half, but we call it log n, right? We call it log n, not exactly half, we call it log n. Doing it over a number, you can basically do log base 2 of that. So if we had an array of range 8, then log 2 of 8, it would take us 3 guesses to get to the number guessed from 1 to 8. Essentially, that's what it means. And log 2 of 100, I don't know what that is off the top of my head, but that's how much it would have taken for this. This is the upper bound, by the way, so maximum 3 guesses. You can examine this by saying 4, let's say our number was 6, 4, then 4 to 8, we would say 2, so we would go 6, and we would do it in maximum of 2, you see. Now another way to think about binary search is, sometimes there is, you would have certain things up to low and then certain things up to high, and the middle of it is what you're trying to find. You can think of it that way as well. So the array can be split into 2 portions. This part is the higher part, this part is the lower part, and you're trying to find the middle. Now square root x, right? Why would we want to do it by instead of doing sqrtx, which is just straightforward, how would we do it with binary search, right? And the idea is the same thing that I gave you pretty much as 1 to 100. If we are given, let's say, this example 16, we consider an array of 1 to 16, because the square root of a number will always be less than the number, right? So a square root of x, like whatever the result y is, y will still be less than x, right? Because we've effectively done x to the power of half. Now we'll consider an array of 1 through 16, and it's the same idea now as this one. We want to figure out a middle such that it hits 16, like the middle squared hits 16 essentially. So we'll consider binary searching on this array 1 through 16. We'll say 1 plus 16 by 2, so 17 by 2. We'll always take the floor of it because the indexes can't be, like the indexes themselves can't be floating values. They have to be integers because you don't access an array by saying 3.5, right? Now 17 by 2, we'll always floor it. I'll just show it like this: 17 by 2. 16 by 2 is 8, so we'll consider that to be the closest. We'll say, okay, we've hit 8. Now what is 8 times 8? 64. Doesn't work, because 64 is way greater than 16. Way greater than 16. Obviously it won't be the answer. So now what we'll do is, since we've determined that 8, portion after 8 is all high, like all of this is high in the array, and we were hitting the middle here, and we realized that anything like greater than or equal to 8 is useless, then we only want to search in this part of the array now, right? This part of the array essentially. And how would we do that? We would assign our new high to be the middle now, and again -1 because we're playing with the ranges, the same thing that I did here, right? We're playing with the ranges. Now it would be 7 because we already considered 8. We don't care about that anymore. And then we would restart our mid to be somewhere in the array. But since we've determined that everything on the right is useless, we'll shrink our array. Basically we'll shrink it, and we'll search on this left part. Now we have 64, right? We hit 64. Bad, we don't want that, so we'll consider numbers from 1 to 7 now. 1 plus 7, 8 by 2, 4. Let's consider 4 now. 4 times 4, that's 16. And what did we want? We wanted 16, right? So we found it, and we simply just returned 4 because that's the thing we wanted. Now I'll show an example of one that doesn't round so perfectly. I'll give 8. I took it from the question. 8, we considered 8. So 1 through 8, again, half it. We'll hit 4. What is 4 times 4? 16. That's greater than 8, right? So we don't want it. We'll shrink the array to be 1 through 3 now. Then we'll find the mid of this. 1 plus 3 by 2. 4 by 2, so 2. Then we'll consider 2 times 2. 2 times 2 is what? 4. Okay, so now we reach this part where we would basically, we've said that the high part at the first step, we've cancelled it out. Then we've considered a new high, right? We've considered a new low, and now the middle that we found is lower than what you're expecting. And what does this question want in particular? We want it to be truncating towards the closest number, so rounding it down, right? So if we have square root of 8, we would round it down to 2, and we found this middle that's less than the value, so we should consider it, right? Because our base would be 0. The square root is never less than 0, right? Any number square rooted is never less than 0, so our base is 0. Like our minimum value would always be 0, because square root of 0 is also 0, so that would be our minimum value. And we would say, okay, we found this 2, right? And the 2 is still following through with 4, and this 4 is still pretty close to the answer, so we'll make our base 2 now, because it gets closer to 8 than 0 does, right? So we'll say, okay, we'll consider 2 as our current answer right now. And the issue with doing it with 2 now is 1 to 1. 1 plus 1 by 2. We'll consider 1. 1 is still far away. 1 times 1 is not greater than our current answer. So our loop itself ends. Our searching itself ends. Alright? Our while condition stops. We are no longer searching. And we're left with this 2. And conveniently, that's also the answer we want. Right? We basically found the closest value to our desired value. Now, if I write this out in code, it will look like we have a low, we have a high. High is set to the x, or the number that they've given, right? Our base is 0, right? Like I said, it will never be negative, so it will always be 0 at the very end. And the other thing to note about binary search is the loop, the while loop, the condition is low is less than or equal to high. Why? Because our pattern considers the idea that low will be on the left side and high will be on the right side. So if at any point in time low exceeds high, then we've done something wrong and we've pretty much messed up. So we should immediately terminate the loop at that point. Now, mid, what did I say middle was? It is basically low plus high of that particular range, and then divided by 2, floor it as well, and then we consider the square of that number, so we'll say mid times mid. Now here comes the conditioning part. Almost all binary search questions will have this loop basically, and I'll show you what I mean. So if square is less than our desired number, which is x, 16 in this case, right? 16, and we've also considered 8. Okay, we'll say if square is less than x, right? But if we wanted our base is 0, right? 2 also is less than 8, but it doesn't mean that we're not considering. We consider it here, right? So we will say, okay, if middle is still greater than our base, then our base will now be the middle, because that is the closest value we've got after 0. And the next thing that we do is we shrink our array, right? The same thing that I did here. If whichever part we find like is not useful to us, we cut that off, we add 1 or we subtract 1, because we've already considered that part of the array. Now we've hit that. Then the second condition is that our square is actually greater than x. If that is the case, then we will just shrink our array as well again. And the only condition that's left after this is equal, right? That means else just means it's equal. Then we would just simply return mid. And once we're done, right? So in the case that 1 plus 1 equals to 1, 1 times 1, and then we would do low equals to mid plus 1, you would basically be doing 1 plus 1, 2, and 2 now exceeds our high that we had mentioned before, which is 1, and this loop would terminate. This loop would no longer run, right? So we just simply return lowest. If we never found the most accurate, then we would return our base, and that's it. That's how you do square root x, binary search explained. Remember, it's basically having which portion of the array, this one or this one.